So, hello everyone. Thanks for joining us here today. It would have been nice, I think, for a lot of us to meet in person at Concordia Loyola. We were gonna order the pizza and everything, but Mother Nature had another plan. But don't worry, for the next series event, I'll make sure everybody gets their free food. I know it's a core staple for the graduate diet. But with all that said, this initiative is funded by the Digital Research Alliance of Canada as part of the DRI EDIA Champions Program. And the big picture of this was for me is to uh, begin at least show that there's demand for learning about graph neural networks, which some of you might have come across now in some publications as as part of a maybe experimental paper. But it's becoming more and more mainstream. But it is still very niche, and it's very much very top, like rank one universities that are really developing it, or it's very much computer scientists who are doing a lot of the work and the publications, and then it's slowly trickling into material science, chemistry, medicinal chemistry, etc. Um, so this first part here is really to show you and explain to you conceptually what is a graph neural network. It is a very dense topic, so we're not going to go fully into all the nitty-gritty mathematics, but we want you to leave saying, okay, I can understand how some of these things are trained and built. I don't think even after this first session you'll be able to get all the data, train a graph neural network. I think that will take the second session, because the second sessions will show you how to take one that's already partially trained, etc. And you can build on top of that. But it is the beginning of a series. With all that said, I'd like to thank our presenters and collaborators. So Jama from University of Montreal / Mila, Drew Wagner from Concordia, and also Mila UDM, I'm not quite sure, and also Mehdi for helping me organize all of this event. So with all of that done, I will now pass it off to Drew. He will begin with the sort of introduction of some of the basics of Python involved in here. I don't know what everybody's level of familiarity is with Python, but we're starting it from the ground zero, so nothing too crazy. All right.
Great, thanks, Amir. So let me get my screen shared here. First of all, can everyone hear me all right? Perfect. Okay, so you should all be able to see my screen in Google Colab. So for those of you who don't know, Google Colab is a service provided by Google that gives you access to a free computing environment. They even give you access to some small GPUs for free and for limited amount of time. And it's a great way to get started with your experiments in GNNs, for example, or in any other sort of machine learning data science task, because it comes with an environment that's already set up for you. You don't have to go through the headache of installation and all of those things that I think we're probably all familiar with. We're familiar with how difficult it can be. That being said, Google Colab is quite limited in terms of how much computing it can provide you. So you definitely won't be able to train a big model on it because of the limited GPU size. And also in the free version, the duration of the sessions are limited. So I'm going to cover how to run things in Google Colab, and then that's what we will use for Jama's tutorial on GNNs. But I will also explain the steps for getting set up on your local workstation. And then I'll briefly introduce how things work on DRAC or Compute Canada, but going into that in detail is not really part of the scope here. So in Google Colab, it comes pre-installed with many many packages, so we can actually list those. Oh, voice is not consistent. Let me see if I can.
Mine's coming in pretty clearly. I don't know.
Coming in clearly? Okay. I can get a little bit closer to the microphone and that should help. Okay, so we can list off the packages in Google Colab. So Google Colab is a mixed media format, meaning there's text cells, which is this one right here. It's just text formatted in Markdown, in case you're familiar with that. And then there's these code cells, and these code cells can be used to execute system commands, but also to execute Python code. So system commands will always start with an exclamation mark. So Python uses, among other things, but the most common package manager that Python uses is called pip. And we can list all of the packages installed there. The first time you run one of these code cells, it will take a little bit of time to run. For all of you guys who are trying to follow along, you'll also see a pop-up asking you to confirm that you want to run anyways, even though you're not the author. And so we can see it's going to list out everything that comes pre-installed, which is obviously a lot of things. Of course, if you're on your local setup, then you won't have all of these packages, and I'll show you how to get set up with them. We can also install new packages. So one package that we're going to need later is called Torch Geometric. And so just as an example, I'm going to show you how to do that. So we can install it like this using the exclamation mark. So that's the giving system commands. But we can also install it in a way that's special for pip, which is with the percentage sign. And that is just going to help avoid some common bugs where certain things will interfere with this environment. So if we run this, it will start the installation process. And so this is a pattern that you'll see very commonly when you open up any kind of notebook. It will often, the good practice is to put all of these installation commands at the beginning, and then that will get installed. So in our case, excuse me. In our case, in this Python tutorial, we're not actually going to use Torch Geometric. We're just going to be using NumPy and PyTorch, which come pre-installed in Google Colab. So we don't even have to worry about installation. There are a couple of interesting things that can be helpful. For example, this all of this output here can be annoying sometimes, especially if you're installing a lot of packages. So you can silence it by adding this percentage sign capture command at the beginning. And you can do that for anything, not just installations. And that way, if you have some maybe data loading process that generates a lot of output that you don't really care about, you can silence it. The idea behind these notebooks, we call them Jupyter notebooks or Colab notebooks, depending on if we're local or in Google Colab. The nice thing about them is they're supposed to be, you're supposed to write it for like an audience, not just for yourself. So you can put your code, you can put your documentation, your explanation, maybe you have some math. We'll see in Jama's tutorial, he has some math for us, some pictures, all sorts of things, and you put it all together. But your outputs of your code also stick around. So if there's any you don't care about, it's helpful to just silence them with capture. Okay, so I'm going to discuss how to set up on your local workstation now, because like I said, Google Colab is very helpful, but it's not going to be sufficient for a lot of larger use cases once you try to go beyond just following tutorials. So one of the things that we want in our environment is we want it to be isolated from our different projects. So these things like when I install Torch Geometric, for example, maybe I have a different project that needs a different version of Torch Geometric, or in any of these things, maybe there's a version that conflicts. And we'll see that's the case often where different libraries require different versions of some of their dependencies. So there's two main software that are used to create these isolated environments. Google Colab does it automatically for you, so you don't have to worry about it. If you have multiple Colab notebooks, they will all be independent. But then when you're dealing with running your own code on your local workstation or in Compute Canada, you basically have a choice of Conda or virtual ENV, virtual environment. Conda is maybe more powerful than virtual environment, but it's also not as lightweight. And so it has some useful features. It can install from a wider variety of sources, has some interesting optimizations for solving your environment to make sure that all of your packages are compatible. But it's heavy, and on, for example, on DRAC, they don't recommend using Conda. I think it's in fact not allowed. So I'm going to cover both of those briefly. So I recommend using Conda for your local environment because it's very powerful. And so in order to install Conda, the instructions, the official instructions, which I've linked here, are very helpful. They provide you the basic installation instructions for Windows, Mac, and Linux. And they also provide these quick start installation instructions. So you can literally copy and paste it into your terminal and install everything. So they have it for Windows Command Prompt, Windows PowerShell, Mac OS, and Linux. And then that will install Conda for you. So in my case here, I have I copied the command for Linux. One thing to note is here I'm showing you guys code, but I've made it not executable because otherwise it will interfere with your Google Colab environment. So for example, if you wanted to install this, you would copy it into your terminal and execute the commands. In my case, it's already installed, so I'll probably get errors. But first it will download, then it will install, etc. It will take a little bit of time, but then you'll have the Conda software installed. There is, however, a step. Just running this is not sufficient. You also have to initialize Conda, and that will make it so that when you open a new terminal, Conda will be automatically available for you to use. So once you've run this installation, you can copy these two commands, and it will initialize Conda for you. In my case, Conda was already installed, so it says there's no changes. Once you've done that, you can create a new Conda environment, and I'll just do it all for you here. Sorry, I'm double clicking. That's why it's glitching like that. Let me copy this. So when you run this command, it's saying Conda. Let me make this a little bit bigger. It's saying Conda create -n stands for name, and it's going to create the environment, an environment named GNN. And that way you can have different environments for all of your projects. And I'm specifying that the Python version should be 3.11 because that's the version that's used in Google Colab, and it will make sure that everything works the way that Gemma intended it in his tutorial, if you want to follow along on your local workstation. It will take some time. It will prepare all the metadata, list all of the packages it's going to install, and then ask you to confirm. You say yes. And then it gives you these helpful instructions to explain how to use your environment. So you copy this command, and that will activate your new environment. By default, when you create a terminal, you'll be in the base Conda environment, and then you can activate the environment for your project on top of that. So when I run this, now you'll see that base has changed. I'm now in the GNN environment, and anything I install will be kept isolated from my other projects. Another thing that's really helpful is this the requirements.txt file. So a requirements.txt file basically lists out all of the requirements that you need for your project, and optionally it can specify specific versions. Then you can commit this requirements.txt file into your, say, your GitHub repository where you're tracking all of your code, or you can share it with other people. And if you specify specific versions, then you can ensure reproducibility across different projects. So in my case, I've already created the requirements.txt. So let me just show you here. This is the file. Cat, if you're not familiar with Linux, just lists the contents of the file. So I've created it for us. And now we can install using pip install -r requirements.txt. And the requirements that I've listed here are actually the requirements that Jama requires in his GNN tutorial that he's going to give us later. So if you follow along with these steps on your local computer, you should have everything that you'll need to then continue with Jama's tutorial. Of course, if you want to use a GPU, then you need to have a CUDA or an NVIDIA GPU on your workstation. However, you'll see that PyTorch also works with CPU, so with just a regular CPU, but training will be very, very slow for large models. So after a little bit of time, it will install everything. It will give us a confirmation of what's been installed, and then your local environment will be ready to be set up. Any questions so far about that?
If anybody has a question, you can also type it in the chat.
Yeah. Okay. While people think, I'll keep going. So this is the process for your local workstation. The emmet library, you'll see that it's going to be used for something in Jama's code, but I think it's mainly kind of to display something, if I'm not mistaken, Jama. The other ones are more specific to machine learning stuff. Excuse me. Okay, so here we set up with Conda, but if you're on Compute Canada, for example, in a cluster, Conda creates a lot of files, and that's not ideal for these shared file systems, and the Conda libraries are not optimized for the Slurm environment. So Drac recommends that you use virtual env instead, and those packages can be installed with pip the same way that we did, because Conda supports both its own installer, but also it works well with pip as well. So Drac provides some really excellent instructions. I've linked them here. And they explain pretty much everything you need, including how to troubleshoot what's going on. The main thing is that you'll have to load up the Python module and to specify the version. So unfortunately, as of now, Drac doesn't support Python 3.11, but the differences are pretty minimal. So most things that work with 3.11 should also work with 3.10. Then you'll also want to include the SciPy stack, because that will come with NumPy pre-installed, SciPy, Matplotlib, a lot of packages that we take for granted in Google Colab, for example. And so it explains how you can load that up here. And so in Compute Canada, there's kind of two different concepts for your environment. There's the system modules, which are loaded with module load. And then there's your Python-specific environment. So it explains that it explains that here. So first you have your interpreter, which is loading up the Python environment. You can load up some pre-installed libraries, which are helpful. And then once you've done that, you create your virtual environment. And that will be done using this virtual env command. And you'll create it. You specify not to download on Compute Canada, because everything that's required is usually already downloaded. And then you give your environment a name here. And the difference between virtual env and Conda is that this environment is not, in Conda, we just gave it a name, but we don't know where that environment's installed. Here, we want to give a directory to where the environment will be installed. Excuse me. Then, once you've done that, the way that we activate the environment is different than with Conda. With Conda, we did, over here, I'll show you again. We did Conda activate, and then the name. In Compute Canada, we use the Linux command source, and then the path where our environment's installed, and then /bin/activate. And basically, that will configure all of the environment variables that are needed so that when we run a command, it uses the correct version for our isolated environment. They recommend that you should always upgrade pip so that you have the latest version in case the Python version that you loaded is out of date or something. And then when you want to exit the environment, you can just run the deactivate command. So I'm not going to go over every single step here because there's obviously a lot of text, and I want to cover just a basic introduction to Python. But when you're getting set up to run jobs in a Slurm-based cluster, you should definitely refer back to this and follow all the steps and understand the different optimizations that they've made. For example, here they're creating the virtual environment in the temporary processing directory. And that's important because we will be accessing many files from this, and we don't want to be doing that through the shared file system because it will slow the cluster down for everyone, and it will slow down your job. And they explain here how to install everything. For example, here they're installing TensorFlow. In our case, we might be installing from our requirements.txt. And then they explain how to update your requirements.txt to contain the exact versions. So in this case, they see after we're installing, now they have the name of the package as well as the exact version, and that will ensure that your jobs will be reproducible. Then they discuss various things about how do you install things which are not directly supported by Compute Canada. So that can be helpful. They explain that in this section. And then at the very end, they give some troubleshooting for how to deal with some common problems. Okay. Let me just take a sip of water.
So Drew, I think there's a question. Someone is asking about emet library in the chat. I don't know what is the question exactly, but
yeah, it's one of the ones listed here, and it's just something that Jama's going to use in his tutorial later. I'm not exactly sure what we're using from there, but we'll see when we get to the GNN tutorial.
Okay, thanks.
Okay, so I could not. Okay, I see. So Python is a really good language for rapid development. It also, in modern Python, is also very performant and can be used for like production-ready code. But one of the hallmarks of Python is its module system, which makes it really easy to install code libraries and then import them into our code. So if you're familiar with Java, you know about the idea of importing code. In C++, you have the include directive. Python makes it very simple to install and comes with many built-in libraries. But as we just saw, it makes it quite easy to install new libraries as well. So here I'm showing a few different ways to import things. Here we're importing a package called NumPy, which comes pre-installed in Google Colab, and it's going to give us some code for dealing with multi-dimensional arrays of data. And rather than having to type out NumPy every time we want to use something from this code library, we're going to import it under the alias MP. And this is the kind of the standard way that you'll see when you're reading other people's code. Then we're importing Torch. Here we're going to import the entire module, and so everything will be accessible under this torch object. And then you can also import specific functions or classes from something. So I'm showing that here. So from the math module, which is a built-in, we're going to import the sign function. And now we can see on this line that everything's available. So if I execute this code, you'll see the output disappears here. It's just booting up. OK, then it runs. It's going to execute all of these imports. And then here, on the whatever's on the last line will get displayed in your output. So here we're separating the things with commas, and it's going to give us 3 outputs. And we'll see what these mean further along in the tutorial. So like any other programming language, Python supports variables, which you use to store data. But the way that variables work in Python is quite different from other languages. In Python, you should think of a variable as a container for some piece of data, not as the data itself. And the reason that's important is because in Python, we don't declare what kind of data we're going to store. There's no strict typing, for example. In Java, if you're familiar, you have to declare that your variable is an integer, or same thing in C++ or C, or most other programming languages. In Python, we just declare the name of the variable, and we just stick some data in it, and it's not important to specify what type it is. And in fact, we'll see that we can actually change the type throughout the programming language, or throughout the program. In Python, everything is what's called an object. If you're familiar with other programming languages, that term will be familiar. And that means that there are no primitive types. So even an integer is an object, even a float is an object, a Boolean is also an object and has methods on it. And then the philosophy behind Python is something called duck typing. So if it quacks like a duck, then it's a duck. And it basically means that many things will not depend on receiving a specific type. They will just depend on receiving an object which supports the functionality that they require. So here I've given an example of how to create various variables. So here we're making a variable named A, and we're assigning the value 5 to it, and it's going to be an integer. Here we're using a real number, so a floating point number, 3.14. Here we have a string. So we surround strings in quotes, and you can also use single quotes. It's the same thing. This is in some languages, single quotes would give you a character. In Python, we don't distinguish between strings or characters. I'm going to try to go a little bit faster as well. I'm noticing the time. You can also create lists using square brackets. You can mix the types of lists. You're not limited to like arrays like in other languages where everything has to be the same. So it's very flexible. You can create Boolean values. Instead of null, Python has something called none. And then you can define dictionaries or hash maps like this. So a curly brace, and then you give a key, and you're mapping it to a specific value. So if I run this, all of these variables will now be available, and I'm listing out the types. So Python uses snake case by convention, which means lowercase, and instead of spaces, we put underscores. Now to show that Python doesn't actually care about the variable type, this was originally an integer, and now I'm going to put a string in it. Python doesn't care. And this can be a blessing and a curse. Sometimes it's helpful, but often it can harm readability. So you should avoid doing this unless you have a good reason for it. OK, so basic operations. Of course, we support all the same things as most other programming languages. You can add variables together using the plus symbol. So if you add 2 integers, naturally you get an integer out. Python will automatically cast things for you. So here b is an integer, but we're going to subtract a float from it, and the result will naturally be a float. Same thing with division. We have an integer, another integer, but if we divide a by b, it's going to cast it automatically to a float and give us the correct answer. Python does, however, have floor division. So it's written using 2 slashes. And that will do the division and then take the floor of it and cast it as an integer, which can be helpful. So 2 divided by 7 divided by 3 and floored will give us 2 as an integer. We can do multiplication using the star symbol, and then exponentiation uses 2 star symbols. So you see that here. Something that's important to note if you're coming from more of a math background where maybe you've used things like Maple, this hat symbol or the caret symbol does not do exponentiation. It implements a bitwise XOR operator. So clearly this is not exponentiation. It's giving us 6, but we should be getting 16. So when you're writing your code, be careful not to forget that, because it won't always give you an error. It will just give you the wrong value. We can also do the mod operator or the remainder operator using the percentage sign symbol. So 10 mod 3 will naturally give us 1. Then there's various different ways to define numbers. We have the standard notation where you list all of the digits. You can also optionally separate with underscores. So that can be helpful for readability to separate the thousands, for example. You can do scientific notation. So 1.88, E stands for 10 to the power of, and then 3. So that will give us this. So it would be the same in scientific notation. It would be 1.88 times 10 to the power of 3. We can also write binary numbers directly by starting it off with 0b, and hexadecimal numbers by starting it off with 0x. And that this shows that all of them are equivalent. This is something that's cool with Python, is you can chain your conditionals. You can't do that in many other languages. So this is checking that A is equal to B and equal to C and equal to D. It's not like this, for example. So that can be helpful. You can do the same thing with inequalities. So you can have like A less than B less than C, for example. Okay, so of course, to write code, we need to be able to control the flow and execute things conditionally. Python, like most languages, has a if statements. We don't need parentheses. We just write if the condition, and then we do a colon. And these colons are a lot like curly braces in other languages. So they're going to begin a block of code, and that block of code needs to be indented with tabs or spaces. The only requirement is that the indentation be consistent. So here, this y equals x will be executed if x is greater than or equal to 0, and otherwise we'll set y equals -x. So that will implement absolute value. And we see that here. So here, this one executed, and here if we set x to -16, the second block will execute. You can also do else if. So you do multiple options. So here, this code will execute if the animal is cat. Otherwise, if the animal is dog, it will do bark, and so on. In this case, exactly one of the blocks will be executed. And note that it's written if, not else if, like in other languages. We can also iterate. So in terms of loops, Python has for each loops and while loops. So in C++ or Java, we'll have constructions like this, where we define some counter and some condition and then some operation you do every loop. Python does not have that. It only has for loops. So in this case, I'm creating variable names. I'm putting a list of our names in there. And then here we'll iterate through each name, each element. So Drew will be stored first in the variable name. And then this block of code will execute and we'll go back. So if I run this, we'll see it says hello Drew, hello Jama, hello Amir, hello Mehdi. So as I said, this kind of structure does not exist. And the idiomatic way to do that in Python is as follows. So for your indexer in range, and range is a special function that will generate these successive integers from 0 up to but not including 6. So when I run, you get 0, 1, 2, 3, 4, 5. As you may have guessed, print is a special built-in function which just prints some output. Even better, there's an enumerate function which allows you to simultaneously iterate over the index of an element and that element itself. So here we do I first is going to be the index, comma, the element. And so it'll say, hello, Drew, your number 0. So that was the Drew was the first name, Jama was the second, etc. There's also while loops. So it will execute repeatedly for as long as the condition's true. So here I'm removing from the list. There's this pop method. And so that means eventually there'll be no names left in the list and the while loop will exit. We can also define functions. So the syntax for that is def, meaning define the name of the function, parentheses, and then the list of arguments or parameters to that function. You use the colon to begin a block of code. And then this return keyword says what value you're going to return from that function call. So if I call it, we'll see here I'm passing I, which is going to store value 0 up till 9. And then it's going to run I times I, basically, and return. Functions should be familiar to you if you've seen other programming languages. There's also positional and keyword arguments. So here we're setting a default value. So the default will be 1. And then when we call it, we can call it like this, where we specify what argument we're passing. But we can also call it positionally like this. Both will work. And then something that's helpful is lambda functions, which are like anonymous functions. So you can write them in line here. And so we're saying we're going to sort this list, and the key is going to be the absolute value. This is a function that gives us the key. I know I'm going very quickly, but I want to get to the interesting PyTorch and NumPy stuff that we'll need for the GNN tutorial. You can also define classes. So that works quite similarly to functions. You have the class keyword, the name of the class, parentheses, and then any parent classes. So we can reuse the functionality from existing classes. So this pattern is something that you'll see a lot if you're using PyTorch, because gnn.module forms the basis for any neural network module. Then where other languages have constructors, Python has an initializer function. So within the scope of the class, we define a new function called init with these double underscores on each side. Self is a special parameter that refers to the current instance. And any method, so any function that's inside of a class must take self. And then all of the other parameters. So here I'm going to define an input size and an output size. Then this super is a special keyword. And when you call it like this, it will give you the parent instance. So it will give us this base module. So then we're going to say first, when we want to initialize, we're going to initialize the base module and then do everything else we want. We can store data onto our class using self dot and then the name of the variable where we want to store the data, and then we assign some value to it. This is a lot like other languages, except we use self, where other languages will use this, for example. And here I'm just going to assign these two values, which store the size of the model. And then I'm going to define a linear layer with input size, output size. I'm going to define some what's called an activation function. You don't really need to, hopefully you understand this, because it will make the GNN tutorial make a lot more sense. But basically, this is just a it's a linear classifier, basically, that a linear module that PyTorch implements, and it will support both computation on CPU and also on GPU. And then we're going to define some activation function. Then there's a special method that's part of this module class called forward, which is where we're going to define how we actually want to compute the output of this model. So we say def forward, self has to be there because it's a method, and then some input. And so what we're going to do is now we can access these modules that we defined earlier. We can access them here. So we're going to say x is equal to self.fc, stands for fully connected. And then we pass the value x to this function. So this is like calling the function. And then we do the same thing with the activation, and we return. So that's how you can do classes. You can, of course, do all sorts. You can add other methods. We could say initialize weights, for example, right? And we can add more code. So classes basically just define a way to group together data and functions which operate on that data. Often your code may raise some errors. For example, in Python, if we try to divide by 0, we get a 0 division error. But sometimes we want to handle those gracefully rather than causing the program to exit. So we can wrap any code that might raise an error in a try clause. So we write try, colon, the code that we put all of the code that might raise an error. And then we use the except keyword. This is like catch in other languages. The name of the exception that we're trying to catch. This is optional. You could catch all exceptions. And so this code will run if and only if this first block of code raises a 0 division error. So of course it will. And when we run this, it will print this code, and then it will assign 0 to x. You might want to assign some other value, maybe a really large number or something. And you can also have multiple exceptions. So this could be something went wrong, some other error that we don't know about, and maybe in that case we want x to be equal to -1. Python has this idea called context managers, which are a really useful feature. And basically what that lets you do is execute some code when you enter this block, and also execute some other code once you leave. And that exit logic will run no matter if you exit normally or if you exit because of an exception. So the way that we access files, for example, in Python is implemented as a context manager. So this with keyword means we're going to do a context manager. Open is going to open a file and return an object. And then we're going to name that file object as f. Then we can, for example, among other things, we can read one line of code from there. And then what happens is once this line of code exits and we get back into the main scope, some code is going to run on this file object. Namely, it's going to close the file handle, like that. So another common pattern that you'll see in PyTorch is this with torch.no grab. And what that will do is disable automatic gradient computation. And that saves us some memory and speeds up our evaluation logic. Internally, this with context works by calling the methods enter and exit on the object that you pass to it. So you can even define your own context managers. Okay, so getting out of the Python basics and into the more interesting stuff, we're going to quickly cover NumPy and PyTorch, which are two libraries for operating on arrays of data, multidimensional arrays of data. And PyTorch also includes some useful library code for machine learning. So here we make sure that NumPy is imported. And here we're going to create an array of all zeros. So we can think of this as a matrix. It's going to be 6 rows by 6 columns. And if we print that out, we see it creates indeed an array, a matrix of 6 rows and 6 columns. This is an object, so it has all sorts of attributes and methods on it that are helpful. One is the shape, so that's going to tell us the size of these different axes. So the first one will be the first axis, which is the rows. The second will be the second axis, the size of the second axis, which is the columns. Also has a data type. And now we're not dealing with Python lists, which can mix different things. We're dealing with highly optimized arrays, which require a homogeneous data type, or sorry, a heterogeneous data type, all the same thing. No, my bad. Homogeneous was right the first time. A little tired today. Okay, so we're not limited to 2-dimensional matrices either. We can do as many dimensions as we want. So here we're creating one that's going to be 3 by 8 by 8. So we can plot out the shape. Indeed, it's that. And we can show it like this. So it's basically, you can think of it as 3 8 by 8 matrices like this. You see? Here I'm going to generate some random numbers. So NumPy supports a lot of useful ways of creating these arrays. Then how do we actually use them? So I said that they're objects and they have methods. So for example, we can call sum, and then we can calculate the sum along some specific axis. So what that will do here is it will add these 3 matrices together element-wise. And the result, as expected, is going to be 4 by 4. Because here we have a 4 by 4 matrix added with a 4 by 4 added with a 4 by 4. And this is the result. So these operations are very, very efficient. And so anytime you're doing data science, you want to be using NumPy or PyTorch, not your own raw functions. There's also other aggregation functions like mean. And in this case, if we don't specify an axis, it's going to take the average over all of these elements. It also supports advanced indexing. So here, for example, we're saying select all 3 of those matrices, but from all of them, select only the first row. And you see that. So now we have the first row from each of the 3 matrices. You can also, for example, select, this is all of the dimensions, and then here we're saying basically the last dimension. So along the last dimension, take the first 3 elements. And this syntax with colons is called a slice in Python. And so there's an implicit 0 here, which means start from the 0th index and count out 3 elements. You can also do Boolean indexing, where you basically provide a Boolean mask, so true or false. And so this will say true, we're going to take that first matrix, and false for the other 2, we don't take them. And so you see it returns one of those 4 by 4 matrices. You can also do integer indexing, where you specify specifically the indexes you want and even change the order. So here we're going to get three rows, but we're going to take the second row, the third row, and then the first row, like this. Most of this all works in PyTorch as well. The main difference with PyTorch is that it supports computations on different devices. So here we're in NumPy, it's using the CPU, but in deep learning, we often want to use the GPU because we can take advantage of its extreme parallelism capabilities. So the main difference when we switch from NumPy to PyTorch is that now we refer to these objects as tensors. So this is a common pattern you'll see where you're going to define what device you want to use based on whether or not CUDA is available. By default, if you don't specify any device when you create your tensor, it will be on the CPU. So this is going to create, like we saw with np.random.rand, it's going to create us so 3 4x4 matrices with random numbers between 0 and 1. And now you see it's called a tensor rather than an array. We can move the tensor to a different device if it's available by doing x.to. So here I'm not connected. I don't have the GPU connected, so it's going to stay on the CPU. But if you were to come into runtime, change runtime type, and let me just do that so you guys can see. I'll change it, give it a second to switch, and we'll execute this again. And now we'll see that once we move, when you request the GPU, it takes a bit of more time to initialize the notebook. So now, because we didn't specify, X is still going to be on the CPU, but now when we move it to our device, it's now going to be on CUDA, which means that any operations on X will be done, and here I should do it like this. Now any operations will be done on the GPU. So we can take the sum, for example, and now something else that changed is in NumPy we called these dimensions of our tensor, we called them axis. Now it's called dim, short for dimension. So this will take the sum along that first dimension, which corresponds to what was it here? This is the 0th dimension. This is the first dimension. So we see we have these matrices that are stacked. The stacking is the first dimension, is the 0th dimension. The rows are the first dimension, and then the columns are the second. So this will be giving us the sum along all of the row, along this way, along the columns, basically. And it's still on the GPU. So if we did more operations, they would stay on the GPU. The other amazing thing that PyTorch supports is automatic differentiation, which allows us to automatically compute the gradients with respect to some function. And we do that by if we want to compute the gradient with respect to x, we're going to set requires grad equals true. Then we do some function. So in this case, I'm taking the average of all of the squares. Then we call that. So this loss, for example, if I can show it to you, will be some number, some tensor, 1.39 in this case. And when I call loss.backwards, that will compute the gradient with respect to the various tensors that we used in the computation. And then we can see that now the gradient is available here, and we can do things like gradient descent. So PyTorch comes with various optimizers. So stochastic gradient descent, Atom, which is an adaptive gradient-based method. And they're all included and implemented in the torch.optim module. And all you have to do is pass them a list of parameters, it's called. So parameters are basically just a wrapping around a tensor that lets PyTorch know that we're going to want to optimize it. So in summary, before I turn it over to Jama, PyTorch has a lot of useful modules. The first is torch.nn. We saw that earlier when we very, very quickly defined a custom model. We used it again here to get the linear layer, the ReLU activation function, etc. So that's all available under torch.nn, which stands for neural network. There's torch.optim, which stands for optimizers, which includes implementations of various gradient descent variations. And then there's a torch.utils.data, will include a lot of code that's helpful for loading up data sets, and data loaders, which allow us to iterate over our data in batches. So if you're familiar with machine learning, you know that stochastic gradient descent operates on just a small sample of the data at a time, and the data loader will implement that for us. Otherwise, there's lots of additional libraries that use Torch, such as Torch Geometric, which we're going to use in Gemma's tutorial for graph neural networks. Torch Vision includes some useful functionality for computer vision tasks. Torch Audio for audio and signal processing. Matplotlib and Seaborn are some useful libraries for generating plots. Pandas is great for working with tabular data. And then Dask wraps some of these other libraries like Pandas and NumPy to handle big data and extreme parallel processing. That's all from my end. I know that was a very quick introduction, but hopefully it will make some of the concepts that Gemma discusses and some of the code that he shows you appear a bit more familiar.